Okay, so in this second lecture chunk, we're going to be talking about armoring, and I got to say, humans interact with waterways through multiple channels. Okay, right? We build roads with culverts and bridges. We have stormwater runoff that we have to put into ponds or discharge as wastewater. We also have runoff from developments or agricultural lands, right? And so we change the landscape in the engineering process, and we have to account for it. And you'll see this especially in the next lecture 15, when we start talking about NR 151. It's just a fact of life, and so we've got regulations in place now to try and better manage our interaction with the environment. We read the paper, the essay by Aldo Leopold. He kind of called for that, but in kind of, I guess you'd say, more holistic ways than maybe this. This is kind of a reactionary, we cause an issue, we're going to try to prevent it before it happens, but we know we're going to create it. So let's talk about armoring, typically below culverts, right? And before we can get into that, I guess the question is, well, when do we have to armor, right? And so we said culvert velocities can be pretty high. They can come out of the culvert pretty high. And when we go through culvert master and we use that, you'll see that indeed we can get pretty high velocities coming out of culverts. And so the question is well, are there certain types of channels or channel materials or channel beds that are going to be native to a landscape, or they're naturally, and we may not have to armor? And the question is, yeah, maybe, right? And so we look here, right? Or even if we're doing a little river engineering, let's say we're kind of putting in some meanders, or maybe doing something to kind of reconstruct a river. The question might be, well, what's a channel velocity that's appropriate so we don't create scour, right? So we don't have to put in some sort of lining or armoring. And in general, for things that are grassline channels, right? So kind of grassed waterways that we're talking about, or rock waterways, these things in general can take pretty high velocities, right? But when we start getting into kind of more natural type landscapes, stream beds that have sand or gravels, right? These things tend to get scoured out because culvert velocities just tend to be greater than this 2 to 6 range, right? If it's pure bedrock, hey, you can let the water flow freely, maybe, if you're not worried about the ecological side and you're just worried about the scour side. If it's igneous or hard metamorphic, it can take pretty high channel velocities before we see any scouring. So in general, we can go to tables like this at some allowable velocities. We could do maybe a little mini study out in the field to ensure it, or it might be dictated by local regulations. So let's talk about armoring via riprap. And, so the question is, well, what is this, right? And so when we have the outlet of a culvert, we're going to tend to have a couple of pieces. We could have a concrete apron that goes, might be included with the head wall that we might need to design. We could also just be placing riprap. So in this case, this design here is calling for a concrete apron right immediately below the culvert exit, followed by an apron of riprap. So this is basically big rock that we're going to put in to kind of knock the velocity out of the water some, but also just to protect that part of the channel. So let's look at the equations that we can use for doing this. So here are a few pictures where you can see kind of what we've discussed, right? So these culverts have a little bit of concrete apron on the outlet structure. This one's got quite a big concrete apron, this box culvert, before it gets down into the natural stream bed where they've probably filled in with this riprap. But in each of these you can see it's big stone right below the outlet. So how do we determine stone size? Well, there's lots of different guidance, and again, you might have to go look. Local ordinances or state highway departments might have their own code for doing this. Here are some equations out of different textbooks that we've found over the years that you could use, and they're appropriate. They may or may not be appropriate for where you're designing, but it gives you a good start, right? So the D50 in feet of your riprap is basically designated by your tailwater, what your flow through the system is, and what the diameter of your orifice or your culvert is, basically, right? And so the thickness of this stone lining, tends to be 3 times the median stone size, so 3 times that D50. That's how thick it should be if you don't have any fabric filter. Otherwise, if you're going to use some filter fabric liner, then it's just twice as thick as the D50 that you're using. That's how thick you want to lay that stone down. So that's how we size the stone. How do we figure out the length of the apron? Well, again, it goes back to this, right? So this length of the apron is going to be dependent on what the flow coming out of the culvert is and what the size of the opening of your culvert is, right, of that exit. And we have two conditions. One, where the tailwater, if that tailwater is greater than half of the diameter of your culvert, then you have to use this equation. But if the tailwater is less, then you need to use a modified version of this equation for calculating the length of the apron. So here are two equations that can be used for calculating the length of the apron. And the last piece is the width of the apron. So if a channel does exist, if you're doing this in a formal natural system channel, then the width of the apron should just always be the channel width. But let's say this culvert, it's kind of discharging into a grassy waterway that's not really a channel, and that water is going to flow and maybe eventually meet up with a channel somewhere. If there's no channel, then again we've got two equations where the width is dictated by the diameter of our culvert and the length of the apron, and we have a condition where the tailwater is greater than or equal to half of our culvert diameter, or it's less than that, right? So we have some options to use. Okay, so we've got equations to use. We've also got nomographs. Now, if you go on the D2L website, there's up there's something for Charlotte, Mecklenburg County, and they have some nomographs in here for determining riprap apron size. So let's look at how we would read this. On the bottom x-axis, you can see we've got discharge down here. And then if you look here, these curved lines are the diameter of the culvert. These straight lines are the velocity coming out, right? And so what we want to do is we want to start out basically by reading up from our discharge to our culvert diameter, or the velocity coming out of our culvert. Once we do that, we can read across and we can calculate what the D50 riprap size is in feet. So in this case, it's going to be just over 2 foot D50 riprap size. So 2 foot chunks of riprap. We've all seen those around. After we do that, we can now figure out what the length of the apron's got to be. In this case, we read up further, all the way up again to the diameter of our culvert. And once we get up to this line, we now read across over here. And in this case, it's saying, the length of our apron should be probably about 55 feet, right? That's going to be the length of our apron. It's in between 50 and 60 here, so about 55 feet. And so in the case of this nomograph, once we know the length of the apron, now it's a pretty simple calculation to compute the width. Now this is again the case where the tailwater is less than half of the diameter of our culvert. We have separate nomographs where if it's greater than half the diameter of our culvert, right? So we can use nomographs, we can use equations. Before you come to class, there's an example in your notes. I would like you to complete the equation part of this. There'll be one of the quiz questions will be on it. It should be pretty straightforward. It's just plug and chug into those equations, try using them, and then we'll try using the nomograph in class and we'll compare and contrast the answers. So the last couple things I want to talk about before this lecture chunk ends is about some other tools that are available. We can use these things called plunge pools, where water exits and we've got an engineered structure that's meant to take that plunging action of water. We're not worried about scour because we might even design this so that you can't scour this pool. But what happens is that high velocity water comes out and it hits a pool of stagnant water, and that really knocks the velocity out of it. And as this pool starts to rise up and fill with water, then we get some overflow down an armored channel out to, in this case, maybe to a culvert that goes under a road. So we can use these plunge pools to really knock the velocity out of the water coming out of a high velocity culvert system. Another device, you might see these in dry washes or desert type environments or areas, or spillways on the downside of dams, would be energy dissipation blocks. So the water is going to come roaring out of here, but it's going to hit these blocks in this stilling basin, and these blocks are basically going to dissipate and take all the energy out of it, and then the water will flow across this armored part of riprap before it enters again maybe a natural system. Okay, so those are the different devices that we have for armoring or dissipating energy. In the next lecture chunk, we're going to talk a little bit more about stream. We're going to talk about stream restabilization in general, and kind of looking at the whole river system, talking about these threshold and alluvial channels, and we'll finish up talking about flexible and rigid liner types.